So in this video we are going to talk about the question in thermal and statistical physics which appeared in JEST 2015 examination. So let's continue with the first problem. The statement is, for the system in thermal equilibrium with the heat bath at temperature T, which one of the following equalities is correct? So here beta is given to be equal to 1 by kT. Okay, so here since in the options we are given the average of various physical quantities, so we will make use of the one of the important results that you might have learned in your theory classes. Okay, the average of a physical quantity y, where y represents any physical quantity, that's given by the expression yi pi and sum over I. So here y stands for the any physical quantity, it could be position, for instance x, it could be momentum, it could be total energy or the potential energy. Okay, and pi is the probability, that's the probability. Okay, so let's call this as equation 1. So now because we are interested in the average of the energy, so we will write that average of E, that is equal to sum over I ei pi. Okay, so that is equal to sum over I ei, and then the we will substitute the definition of the probability, which is equal to exponential minus beta ei, and then divided by sum over I exponential minus beta ei. Okay, so let's call this as our result 2. Okay, so now we are interested in evaluating the differential of the average energy with respect to beta. So what we are going to do is we will evaluate this quantity curly beta or dd beta of average energy. Okay, so since this requires a little bit more space, so I'm moving to the next page. So just 1 second please. Okay, so here the quantity dE by d beta, so that is we are interested in evaluating dd beta of average of E. Okay, so if you just take a look at the expression that we obtained, so here we will follow the rule that differential of f of g dash, that is equal to g f dash minus f g dash upon g square. So here f is this, the numerator that represents the f, and the denominator represents the g. So we will apply this rule here in equation 2 and then write the differential. Okay, so first I'm writing the g, which is denominator. So in the denominator we are having I exponential minus beta ei, that's g, and then multiply by f dash. So f dash, so now it's a differential of the numerator, which is ei exponential minus beta ei, and again the differential of this quantity. Okay, sorry, the differential of the exponent. Okay, so that is with respect to beta, that will give us a ei. Okay, now gf dash is over, now minus fg dash minus, now let's first write f, which is sum over I ei exponential minus beta ei. So f is over, now differential of g, so sum over I exponential minus beta ei, and then multiply by minus ei. So gf dash minus fg dash upon g square, which is sum over I exponential minus beta ei and its square. Okay, now we are going to separate these two terms. Okay, so this is equal to, so first term will become, so here we are having a negative sign here, so negative I'm taking outside, and then ei square, one ei here and another here, so ei square exponential minus beta ei. Okay, and then one of the summation will cancel with one of the summation in the denominator, so ultimately we will be left with only term exponential minus beta ei. That's the first term. Okay, now the second term, so one minus here and another minus here, so that will make it a plus sign. Okay, and then inside the bracket we can rewrite this as, so this is EI exponential minus beta EI, and then if you bring this here, this is again EI exponential minus beta EI. So minus sign we have already taken into account, so this comes out to be equal to EI exponential minus beta EI, and then divided by sum over I, here also exponential minus beta EI, and it's square, because we are having the individual term two times. Okay, so that means if you just again make use of the definition of the average. Okay, so this result I'm talking about. Okay, by making use of this result, again I can rewrite this as, because here instead of the physical quantity it's EI square, so then I will write it as a negative sign outside and then average of E square. Okay, and then plus, now the second this expression, this is equivalent to the average of E, and but now it's square. Okay, or this is equal to average square minus square average. Okay, and then if you take a look at the options, so it matches with option A, so therefore option A is the correct one. Let's continue with the next problem. An ideal gas is compressed adiabatically from an initial volume V to a final volume alpha V. Okay, and a work W is done on the system in doing so. The final pressure of the gas will be how much? Okay, gamma is given to be ratio of Cp by Cb. So first of all, we must have an idea about the work done in an adiabatic process. So for instance, let's say the system changes its equilibrium states from temperature T1 to T2, or we can say from initial parameter P1 B1 to P2 P2. Okay, so in that case the work done during an adiabatic process W, that is equal to NR upon gamma minus 1 into T1 minus T2. Okay, or this can be also rewritten in terms of pressure and volume, as because here we are interested in the expression for the work done in terms of pressure and volume, because that's the information given to us. Okay, so that is equal to 1 upon gamma minus 1 into P1 B1 minus P2 B2. Let's call this as equation 1. So here we are given that V1, that is equal to V, and V2, this is alpha times initial volume. Okay, so now because we have to find what is the pressure P2. Okay, so in that case what we are going to do, we will eliminate P1 from equation 1 first. So that means we are going to write P1 in terms of P2 in equation 1, and then we will obtain the final expression for pressure P2 from equation 1. Okay, so eliminate P1 from equation 1, and this we can do with the help of that adiabatic relationship, that is P1 B1 power gamma, that is equal to P2 B2 power gamma. Okay, so from here I can write P1 in terms of P2. Okay, so P1, that is equal to B2 by B1 power gamma and multiply by P2. Okay, so B2 is alpha times V, alpha V upon B1, which is B, its power gamma, and then multiply by P2. So that means P1 is equal to alpha times alpha power gamma multiply by P2. Okay, so let's call this as equation 2. So now substitute the value of this P1 in equation 1. So then we will obtain expression for the work done W, that is equal to 1 upon gamma minus 1. Now it's P1. Okay, so P1 is this expression, so P1 B1, that is alpha power gamma P2, and then multiply by B1, which is B. Okay, minus P2. So P2 is, P2 as it is. Okay, and then B2, so B2 is alpha times V, that's B2. Okay, so from here we will take the common terms outside, so P2B is common in both of these two expressions. So P2B upon gamma minus 1, and then inside the bracket it's alpha power gamma minus alpha. Okay, so this can be rewritten as from here I can write the expression for P2, that is equal to W by B, and then gamma minus 1 upon alpha power gamma minus alpha, and this can be further written as W by B 1 minus gamma upon alpha minus alpha power gamma. Okay, and this matches with the our option C here. Okay, so therefore option C is the correct one. So let's continue with the next problem. The statement is, a particle in thermal equilibrium has only 3 possible states with energy minus E, 0 and E. So let's draw the corresponding given energy states. So these are the 3 energy states, okay, with energy minus E, 0 and E. Okay, if the system is maintained at a temperature T, so we are given the condition that temperature T is much larger than E upon kb. Okay, or we can say that this implies E upon kbt, that is much smaller than unity. Okay, so then the average energy of the particle can be approximated. So that means we have to look for the expression for the average energy of the particle. Okay, so we are going to solve this problem with the help of the partition function approach. Okay, so the partition function for the given system can be written as Z, that is equal to, because it's a discrete energy spectrum, so Gi exponential minus beta EI. Okay, I taking value from 1 to 3 because only 3 levels. Okay, so here degeneracy, because nothing is given about the degeneracy, so we can take it to be unity. Okay, so that means the partition function will be G, it's going to 1 for all the states, so exponential minus beta multiplied by energy. So when we will multiply minus beta with minus E, so that will give us the beta E. Okay, now for the second term, exponential minus beta multiplied by energy 0, so that will give us 1. Okay, and then the third term corresponding to the upper energy level E, so exponential minus beta E. Okay, this is equal to, you can write it 1 plus exponential minus beta E plus exponential beta E. So that's the partition function for this system. So from the partition function we can determine the average energy, which is related to the partition function as E, that is equal to minus curly beta of ln Z. Okay, or that is equal to minus curly beta of ln 1 plus exponential minus beta E plus exponential beta E. Okay, so this upon differentiation, so this will give us minus 1 upon 1 plus exponential minus beta E plus exponential beta E, and then the differential of these terms with respect to beta. Okay, so the first term will give us exponential minus beta E, and then again minus E plus exponential beta E, and then E. Okay, so this can be rewritten as, so this is equal to minus okay, so let me write on the left hand side, so average of E. Okay, so we will take minus E outside, and then inside the bracket we will be left with okay, minus exponential minus E upon kt. Okay, and then the second term plus exponential E upon kt, and then this term is divided by 1 plus exponential minus Ey kt plus exponential Ey kt. So here we are going to apply the approximation, because it's given that Ey kt is much smaller than unity. This implies Ey kt square it's going to be even smaller than Ey kt. Okay, so therefore we will neglect the higher order term upon expanding the exponential term. Okay, so therefore this reduces to, this is equal to minus e, and inside we will have exponential minus Ey kt, so that will give us 1 minus Ey kt, but with the negative sign outside, so it will be minus 1 and then plus Ey kt, and then expansion of the second term, so 1 plus Ey kt, and in the denominator we will apply the same concept here, 1 plus, now exponential can be written as 1 minus Ey kt, and then plus 1 plus Ey kt. So Ey kt will cancel, and here 1 will cancel with 1. So upon solving, this comes out to be equal to minus 2 e square upon 3 kt. Okay, so therefore option B is the correct one here. So let's take a look at the next problem also. The statement is, the black body at temperature of 6000 Kelvin emits radiation whose intensity spectra peaks at 600 nanometers. So let's write the information that is given to us. Let's say that T1 is equal to 6000 Kelvin and lambda 1, that is equal to 600 nanometer. Okay, if the temperature is reduced to 300 Kelvin, so that means we are given that temperature is now reduced to 300 Kelvin. So temperature has changed from T1 to T2. Now the question is, what is the corresponding value of lambda 2? So that we have to find out. So here we are going to apply the Wien's displacement law, that is Wien's displacement law. According to this law, lambda, the wavelength at which the emission is maximum, and multiply the corresponding temperature, that is equal to constant. So that means for two different temperatures, so lambda 1 T1, that will be equal to lambda 2 T2. So this is given to us, this is given to us, we have to figure out what is lambda 2. So lambda 2 will be T1 upon T2 multiplied by lambda 1. So from here, okay, so simply substitute the value of given parameter. So lambda 2 is equal to 6000 divided by 300, and then multiply this by 6, okay, so multiply by T1, okay, lambda 1, so that is 600 nanometer. Okay, so upon solving, this will come out to be equal to 12,000 nanometer, and that's nothing but 12 micrometer. Okay, so therefore option B is the correct one here. So let's continue with the next problem. The statement is, electron of mass m in a thin long wire at temperature T follow one-dimensional Maxwell velocity distribution. The most probable speed of this electron is how much? Okay, so let's first write the expression for the Maxwell-Boltzmann velocity distribution in one dimension, and that is given by f of Vx, and that is equal to m upon 2 pi kBt 1 by 2 exponential minus m Vx square upon 2 kt, and then dvx. Okay, so this distribution, it looks like this. Okay, it's symmetric with respect to x. Okay, Vx along positive direction and along negative direction. Now in order to find the most probable speeds, okay, so that means what the strategy that we adopt, as we did in the three-dimensional case also, we are going to maximize this function with respect to velocity. Okay, so that means dfv upon dbx, that is equal to 0. So that will allow us to determine the most probable speed for the one-dimensional probability distribution function. Okay, so by applying this condition here on this function, so what we obtain is this, the constant term as it is, m upon 2 pi kt power 1 by 2, and then differential of exponential term with respect to Vx. Okay, so that will give us exponential minus m Vx square upon 2 kt, and then minus again the differential of the exponents. Okay, so that means minus m upon 2 kt and then multiply by 2Vx. Okay, and that should be equal to 0. Okay, so from here we conclude that Vx, which is equal to the most probable speed, okay, and that is equal to 0. So therefore the correct option is C here. So let's continue with the next problem also. Okay, the statement is the entropy temperature diagram of two cornered engine A and B are shown in figure 4. So sorry, in this figure here. Okay, here. Okay, the efficiencies of the engine are eta A and eta B respectively. Which one of the following equalities is correct? Okay, so here we are given the temperature entropy diagram for two different engine A and B. So please pay attention to the axes which are given to us. Okay, the temperature axis it's along the x direction, and entropy axis it's along the y direction. So okay, so since the way the diagram is drawn here, all the boxes, they are of equal area, so I have just labeled them as 0, 1, 2 and 2, 3 and so on. Okay, so in order to determine the efficiency of a heat engine by knowing the TS diagram, the general expression that we use, eta, that is equal to the work out divided by heat input Q1. Okay, and that is equal to Q1 minus Q2 upon Q1. So basically Q1 minus Q2, that is the area bounded by TS diagram, and divided by the heat that is given to the working substance at higher temperature. Okay, so here if we just take a look at the diagram A, the TS diagram for the engine A. So here this corresponds to the upper line, it corresponds to a temperature of 2T, and this corresponds to a temperature of T. Okay, and similarly the temperature corresponding to the upper along the entropy axis, it is 4S. I'm talking about this point, and here corresponding to this line it is 1S. Okay, so now we can quickly determine the area which is bounded by the TS diagram for engine A. So let's see how we can do that. So for the engine A, if I'm denoting the efficiency as eta A, so that is equal to the area bounded by the TS diagram, this TS diagram, and that is equal to 2T minus T. Okay, so 2T minus T, so that will give us this length on the temperature axis. Okay, and then 4S minus, sorry, not 4S, this is, yes, 4S minus, there is something wrong here. Okay, this is 4S minus 1S. This will give us the delta S. Okay, so 4S minus S. So this is basically this length. Okay, so that will give us the area of the TS diagram. Now divided by Q1. So Q1 is determined by the high temperature line. Okay, so that corresponds to a temperature of 2T. Okay, so that means 2T Q1, that is equal to 2T TDS. So 2T and then the corresponding change in entropy, and corresponding change in entropy is governed by this line from here to here. Okay, so that is equal to 4S minus 1S. Okay, so this will cancel with this quantity, so ultimately this is equal to 2T minus T, that is T, divided by 2T. So that means eta A is equal to 1 by 2. Similarly, we can determine the efficiency of heat engine B, that is equal to, again now we have to consider this difference. Okay, so that is equal to 4T minus 3T, that will give us this length. Okay, and then we require this length which is same as in the previous case. Okay, so that is 4S minus 1S. Okay, so that now this product will give us the area bounded by the TS diagram. Now divided by the corresponding Q1. So Q1 here will be determined by this line. Okay, so here the temperature corresponds to 40. Okay, 40, and then delta S. So for S minus 1 S. Okay, so here again this will cancel with this, so this will give 3s, and then 40 minus 3t, so that is 1t. Okay, and then divided by 40. Okay, so that is equal to 1 by 4. So therefore we notice that eta A is larger than eta V, or what you can do is eta A, we are asked the ratios basically. Eta A upon eta V, that is equal to 1 by 2, that's eta A divided by eta V, that's 1 by 4, so that is 4 by 1, so that is equal to 2, or eta A, that is equal to 2 times eta B. Eta A is equal to 2 times eta B, or eta A, yes, it's D. Eta A is 2 times eta B, so that is option B, D is the correct one.